Low Earth orbit satellite megaconstellations promise to revolutionize the future of communications and Earth observation and monitoring. For instance, in what concerns communication, they enable global connectivity with low latency, high capacity, global coverage and low power consumption. Due to the low coverage of a single satellite, these constellations employ a very large number of small and simple satellites. Despite that, the current tracking, telemetry and command system does not differ from the one employed for a single satellite. This centralized architecture requires several ground terminals and severe computational power, which is very expensive and challenging to maintain in practice, threatening the economical viability of these ventures. Therefore, a paradigm shift from an operational standpoint towards on-board distributed solutions is inevitable. A megaconstellation is composed of several shells. The shape of its shell must be maintained to avoid collisions and maintain global coverage. The maintenance of semi-major axis, eccentricity, and inclination are controlled independently between satellites, defining a decoupled component of the tracking objective. But the maintenance of mean argument of latitude and longitude of the ascending node is coupled between satellites, defining a coupled tracking component. Note that such a relative strategy is fuel-saving, since the satellites do not fight common disturbances. We can now formulate the overall cooperative shapekeeping task as a very large-scale control problem. It resorts to local laser communication between satellites in a decentralized framework, thereby reducing the communication pressure tremendously. And it is subject to constraints for a feasible distributed on-board implementation, for which no state-of-the-art solutions exist. To solve this problem, leveraging concepts from optimal control theory, we propose a convex relaxation approach to obtain a global synthesis procedure, which can, then, be decoupled, introducing a thoughtful approximation. Finally, a scheduling procedure was proposed to allow for a real-time on-board operation. Our solution was validated in a high-fidelity orbital propagator, yielding very promising performance. Despite the large initial error, meter-level accuracy is achieved. To conclude, a novel solution to a previously unsolved problem was devised to enable future space exploration and exploitation.